I'm Rex, and today I'm sharing our paper, Tracking Anything with Decoupled Video Segmentation. We are interested in the problem of universal video segmentation. Inspired by the recent progress in universal image segmentation, such as Segment Anything or Grounded SEM, we asked this question: can we extend these methods to videos? Here is one of the example outputs of our method. Given the text prompts, guinea pigs, and chickens, our method is able to detect, track, and segment these target objects without ever being explicitly trained on these object classes. We can also perform different types of video segmentation tasks by simply swapping the image model. Here we show an example of automatic video segmentation without needing any user input. We achieve this with a decoupled video segmentation framework, which we call DIVA. DIVA combines a task-specific image model, such as SEM, and a task-agnostic temporal propagation model, such as XMAP. To combine them, DIVA contains two main components: consensus and merging. The resultant method is used for universal video segmentation. DIVA starts by applying an image detection model on the first frame. The detections are used to initialize the memory bank of XMAP, which in turn propagates the segmentation to future frames. Every so often, new objects might have come into the scene, but it cannot be tracked by XMAP since they were not included in the memory. Therefore, we will have to reapply the detection model to detect these new objects. In order to obtain less noisy detections, we perform consensus routing across a few different detections from different frames. The denoise consensus is then merged with the propagation result. How do we find this consensus? Let's start with the representation. As input, we have a set of detected segment proposals, the PFIs. And each of those segment proposals suggests the possibility of there being an object at a particular location. Our goal is to select a subset of valid proposals as output, as shown below. We have two main criteria for selecting the proposals. The first is a support criterion. We want to select proposals that are supported by the other proposals, with the support being defined by having a high intersection over union score. In this example, the top left segments are supported by all the detections and should be included as the output. The bottom purple proposal, on the other hand, is a lone proposal that is not supported by anyone. Therefore, it should be ruled out as a noise. The second criterion is to avoid overlap. That is, the selected proposals should not significantly overlap with each other. This is based on the simple assumption that each pixel in the output space should be occupied by one object only. In this example, this means only one of the three top left segments should be selected as the output, as they significantly overlap with each other. In summary, we want to select a subset of segment proposals from the end input using the support and the no overlap criteria. In practice, this is implemented with an integer programming optimization. Finally, we merge the consensus with the propagation result. This is done by following three simple rules. First, segments that agree with each other, that is, segments that have a mutual value over 0.5, should be merged together. Secondly, detections that are not matched with any propagated segments should be added as new objects. Finally, unmatched propagated segments should pass through to the output. Additionally, we keep a countdown on these segments so as to delete them if they continue to fail to match for L consecutive times. Our code and demo are available online. Feel free to test DIVA on your own data.